Welcome back, everyone, to the deep dive. Today, we're going to be taking a look at a really cool AI project. DeepCoder 14B preview. And it's all about like making AI that can write code.
Yeah, exactly. And what's cool about DeepCoder is it's really small. For the kind of performance that it gets, it's only 14 billion parameters.
Okay.
So, that puts it in kind of like the same performance bracket as these huge models like O3-mini. And it's much, much smaller.
Yeah. It's like getting a car that's like super fuel efficient that can still like win the race.
Right. Exactly.
Yeah. So we've seen AI getting really good at math lately, with models like DeepScaler and such. But coding has seemed to be kind of lagging behind.
Right.
What do you think is like the main reason for that?
Well, I think a lot of it has to do with data and the challenges of curating data for reinforcement learning.
Okay.
Because, in RL, you need to give the model a very clear reward signal. Did it do the right thing or not? And with coding, it's not always super straightforward.
Yeah.
The data sets that are out there, a lot of them have problems with the tests. Like the tests might be buggy.
Oh, yeah.
There might not be enough tests, or maybe the solutions are even just wrong.
Interesting.
And so it's very hard to train these models to do well because you don't know whether they're getting the right reward or not.
So that's why DeepCoder is so cool. It seems like they were able to solve those data challenges. And get this model that's both really high performing and really efficient.
Right.
So what we're going to do in this deep dive is really look at DeepCoder. How they curate the data, how they built the reward system, the different training tricks that they use, and ultimately like how it stacks up against other models and how well it works.
Exactly.
Yeah. All right. So let's jump into it. Let's start with the model itself. So DeepCoder 14B preview. Yep. It's a 14 billion parameter model.
That's right.
It's not totally new. It's actually fine-tuned from an existing model.
Yeah. So it's actually fine-tuned from this model called DeepSeek R1 Distilled Qwen 14B.
Okay.
Using distributed reinforcement learning.
So that's basically like having a bunch of different AI agents all learning at the same time.
Right. All working together to improve the model.
And that helps to speed up the training process, right?
Yeah, exactly.
Cool. So they report a 60.6% pass at 1 accuracy on LiveCodeBench. So for people who aren't familiar with that, like what is LiveCodeBench?
So LiveCodeBench, or LCB for short, is this really popular benchmark for evaluating how well AI models can solve coding challenges.
Okay.
It's kind of like the gold standard.
Gotcha.
And pass at 1 means that the model generated a correct solution on its very first try.
Gotcha. So 60.6% of the time, it was able to generate a correct solution on the first try?
That's right.
It's pretty impressive.
Yeah, it's pretty impressive, especially because that's an 8% improvement.
Okay.
Over the base model that they started with.
Wow. Okay. That's a pretty significant boost.
It is. It is. And this is just with 14 billion parameters, right? So for context, some of these big language models out there can have hundreds of billions of parameters, even trillions of parameters.
Right.
And DeepCoder is performing at this high level with just 14 billion.
So it's super efficient, right? Like it's getting a lot of performance out of a relatively small number of parameters.
Right. Exactly.
Yeah. And what's also cool about this project is that it's completely open source.
Yes. Yeah, it's really great for the research community.
Yeah. So they've released the code, the data, the training logs,
everything,
all the system optimizations that they made. So that's like a huge boon to anyone who wants to reproduce their results or maybe even build on their work.
Right, exactly. I mean, it's really great to see that level of transparency in this field.
Yeah.
Because it allows everyone to learn from each other and really push the field forward.
All right. So let's talk about the data.
Okay.
Because you mentioned earlier that data is like a huge challenge for reinforcement learning in code generation.
Right.
So how did the DeepCoder team go about selecting and curating their data?
So they actually started by looking at a bunch of different data sets.
Okay.
Some of the popular ones out there, APPS, Taco, Code Contests, Code, LeetCode. Yeah. But they found that a lot of those data sets weren't actually that great for reinforcement learning.
Gotcha.
They might have been too easy. Some of them have those same data quality problems that we talked about before, right? Yeah. Like, buggy tests, not enough tests.
Yeah.
And so they ended up going with a much smaller set of very high quality data sets.
So what did they end up using?
So they used problems from Taco Verified, which is a really popular benchmark in the program synthesis community.
Okay.
They also use problems from Prime Intellect's Synthetic 1 dataset.
Okay.
And then they also use problems from LiveCodeBench.
Uh-huh. Okay.
But specifically, submissions from May raced 2023 to July 31st, 2024.
Okay.
And, you know, one of the reasons why they chose this time period is because they wanted to make sure that their test sets didn't overlap with their training set.
Gotcha.
So they had this like separate test set from LiveCodeBench that was from August 1st, 2024 to February 1st, 2025.
Right.
And then also another separate test set from 57 Code Forces contests.
Gotcha. So they were really careful about making sure that their test sets were like truly unseen data.
Exactly.
Yeah. And how did they go about filtering like the data that they chose, like, you know, to make sure it was high quality?
So they had a really rigorous, 3-stage filtering pipeline.
Okay.
So first they had what they called programmatic verification.
Okay.
And that basically meant for every single problem, they ran it against an official solution.
Okay.
That was provided by the dataset creators. And they only kept problems where that official solution passed all the tests.
Right.
So that just ensured that, you know, the problems themselves were well defined.
Right.
And solvable.
Yeah.
They actually wrote a script, test rewards .py, which did this programmatic verification automatically.
Oh, cool.
So that was the first stage. The second stage was test filtering.
Okay.
And here they set a minimum number of tests for each problem to be included.
Okay.
And that number was 5.
Gotcha.
Because what they found was that if you have too few tests, then it can lead to this problem called reward hacking.
Okay.
Where basically the model learns to game the system, and it might not actually be solving the problems correctly. It might just be
memorizing.
Yeah, like spitting out something that knows will pass those limited number of tests.
Yeah, that makes sense.
Yeah, so they made sure that all the problems had at least 5 unit tests.
Okay.
And then the final stage of the filtering was deduplication.
Okay.
So they removed any duplicate problems that might have appeared across their different training sets. But also they made sure that there were no overlaps between their training set and their test sets.
Okay.
Which, you know, as you mentioned before, is really important to make sure that you're actually evaluating the model's ability to generalize to new problems.
So after all this filtering, how many problems did they end up with in their final training set?
So after all that, they had 24,000 problems.
Okay.
Which is actually not that many.
Yeah, it's pretty small compared to some of the data sets that are used for like these large language models.
Right.
Yeah.
Yeah. I mean, some of these pre-training data sets can have, you know, trillions of tokens.
Yeah.
But here they're really focused on quality over quantity.
Gotcha. Okay. So now let's talk about like how they actually train the model.
Right.
So they're using reinforcement learning.
Yep.
And they need some way to tell the model whether the code it's generating is good or bad.
Yeah.
So how did they design the reward system?
Right. So this is where they use what they call a code sandbox environment.
Yeah.
And this is just a safe and isolated space where they can run the code that's being generated.
Okay.
And evaluate against the tests.
Gotcha.
And they actually use 2 different code sandboxes.
Oh.
One is called Together Code Interpreter.
Okay.
Which is really fast and efficient.
Okay.
And it's also really cheap. It only costs about 3 cents per problem.
Oh, wow. Okay.
And they were able to scale this up to run like hundreds of sandboxes in parallel.
Gotcha.
Which is really important when you're doing reinforcement learning because you're constantly generating code.
Right.
And you need to evaluate it really quickly.
Gotcha.
And then the second code sandbox that they used is what they call Local Code Sandbox.
Okay.
And this basically just spins up a separate Python process that runs the code.
Okay.
And it's designed to be exactly the same as the official LCB repository.
Okay.
In terms of how it evaluates the code.
Gotcha. So that makes sure that, you know, their results are actually comparable to the official LCB leaderboard.
Exactly.
Yeah. Okay. So now that they have these environments set up where they can run the code, how do they actually like define the reward?
Right. Right. So they use a very simple reward signal. They call it a sparse outcome reward model.
Okay.
Or ORM for short.
Okay.
And it's a binary reward signal.
Okay.
So it's either 1 or 0.
Okay.
1 means that the code passed all of the tests.
Okay.
And 0 means that it failed at least 1 test.
So no partial credit?
No partial credit, yeah.
Gotcha.
And the reason why they do this is because they found that partial credit can actually lead to some of those reward hacking problems that we were talking about before.
Gotcha. So it's like, you really want to encourage the model to like fully understand the problem and generate completely correct code.
Exactly. Yeah. You want the model to actually be able to solve the problem, not just game the system and get partial credit. And for problems that have a lot of tests, you know, like sometimes you might have hundreds of tests for a single problem. They don't run all of them during training. They only run the 15 most challenging tests.
Okay.
Which they define as the tests with the longest input string.
Okay.
And that's just because, you know, longer input strings generally correspond to more complex test cases.
Gotcha.
And so it's more computationally efficient to just focus on those.
Yeah, that makes sense. And they also have like a timeout mechanism, right? To make sure that the code doesn't like run forever.
Right. So each test has a time limit. Usually it's like between 6 and 12 seconds.
Okay.
And if the code takes longer than that to run, then it gets a reward of 0.
Gotcha. Okay. So we talked about like the sandbox environment, the reward system. Yeah. Now let's talk about like the specific algorithms that they use to train the model. So they mentioned GRPO plus and iterative context lengthening.
Right.
So let's start with GRPO plus. Like, what is that?
So GRPO plus is basically an improved version of this existing reinforcement learning algorithm called GRPO.
Okay.
And the DeepCoder team made a number of improvements. Based on their experience and also some insights from another algorithm called DLPO.
Gotcha.
And some of the key improvements that they made were they removed the entropy loss.
Okay.
They found that entropy loss was often causing instability during training.
Gotcha.
You know, the entropy would like spike really high.
Okay.
And then suddenly collapse.
Okay.
And it was just kind of causing problems.
Yeah, that makes sense.
So they just removed it.
Gotcha.
And that seemed to help a lot.
So is entropy loss like not a good thing in general, or is it just like in this specific...
Yeah, it's not necessarily bad.
Okay.
It's just that in this particular setting, it was causing problems.
Okay.
And it turned out that they didn't really need it.
Gotcha.
Like the other mechanisms in their training algorithm were already providing enough exploration. So yeah, they just got rid of it.
Okay. What other changes did they make?
So they also removed the KL loss.
Okay.
Which is another thing that's often used in reinforcement learning.
Okay.
And KL loss is basically a way to measure how much the model's behavior is changing from one iteration to the next.
Okay.
And it's often used to like constrain the model and make sure that it doesn't deviate too far from its initial behavior.
Okay.
But the DeepCoder team found that removing the KL loss actually helped their model to learn faster.
Okay.
And to explore a wider range of possible solutions.
So they were like kind of giving it more freedom to like go off and explore.
Yeah, exactly.
Yeah.
They also made a couple of other changes that were inspired by the DPO algorithm.
Okay.
One of them is called overlong filtering.
Okay.
And the other is called clip high.
Okay.
So overlong filtering is basically a way to make sure that the model can still reason over long sequences, even when it's being trained on shorter sequences.
Okay.
So during training, if the model generates a sequence that's longer than the current context length, they just mask out the loss for the part of the sequence that's longer than that.
Gotcha.
So they don't penalize the model for generating a longer sequence.
Gotcha. So they're kind of like encouraging it to still like, you know, think big, even if it's only being trained on like shorter sequences.
Exactly.
And that's really important for coding, right? Because code can be really long and complex.
Right. Exactly. And so, you know, if you're only training the model on short sequences, then it might not learn how to generate longer sequences.
Right, right.
And then clip high is basically just a way to adjust the upper bound of the surrogate loss function that's used in GRPO and PPO.
Okay.
And they found that increasing this upper bound helped to encourage the model to explore a wider range of action.
Gotcha.
And it also helped to stabilize the entropy, which is something that we talked about before as being a problem.
Right, right.
So yeah, those are some of the key improvements that they made.
Okay. So now let's talk about like the context length and this idea of iterative context lengthening.
Right.
So what is iterative context lengthening?
So iterative context lengthening is this training technique where you gradually increase the length of the sequences that the model is trained on.
Okay.
So you start with a short context length, and then as the model gets better at solving problems in that context, you increase the context length.
Gotcha.
And this is something that was done in the DeepScaler project, which, we talked about before, was a really successful project in the realm of mathematical reasoning.
Right.
So they were able to, increase the context length all the way up to 24,000 tokens.
Okay.
And they saw improvements in performance all along the way.
Okay.
So the DeepCoder team wanted to try this with their 14 billion parameter model. But they ran into some problems.
What kind of problems?
Well, the main problem was that their 14 billion parameter model was already much better at reasoning than the smaller 1.5 billion parameter model that was used in DeepScaler.
Okay.
So to actually improve its performance, they needed to give it harder problems.
Okay.
And harder problems generally require longer sequences to solve.
Gotcha.
And they actually found that initially trying to train with a shorter context and then penalizing the model for exceeding it actually hurt performance.
Interesting.
It made the model worse.
Okay. How come?
Well, basically what was happening was that the model would start to generate shorter sequences because it knew that it was going to be penalized for generating longer sequences.
Right.
And that actually prevented it from learning how to solve those harder problems that required longer sequences.
Gotcha.
So that's where overlong filtering came in.
Okay.
So by using overlong filtering, they were able to train the model on shorter sequences without penalizing it for generating longer sequences.
Gotcha.
And that allowed the model to still learn how to solve those harder problems.
So they were able to have their cake and eat it too.
Yeah, exactly.
Yeah. So what were the specific context lengths that they used for training?
So they started with a context length of 16,000 tokens.
Okay.
And then they increased it to 32,000 tokens.
Okay.
And they actually found that when they evaluated the model with a 64,000 token context, it performed even better.
Oh, wow. So even though it was only trained on a 32,000 token context,
it
was able to generalize to a longer context.
Yeah, exactly.
Yeah.
And it actually outperformed the base model by a significant margin. At that longer context length.
Okay. That's really cool. And I know they also included a figure in the paper that shows the average response length increasing during training, which suggests that the model was actually learning to generate longer, more complex code.
Yeah, exactly. Initially, the average response length was around 8,000 tokens.
Okay.
And by the end of training, it was up to 17,500 tokens.
Oh, wow.
So the model was definitely learning how to generate longer and more complex code over time.
Yeah. I really like that quote that they had in the paper. Baby, there ain't no mountain high enough, ain't no context long enough.
Yeah.
Which I thought was really funny.
Good one.
Yeah. But it also highlights this ongoing challenge in AI, right?
Yeah.
Of being able to reason over these longer and longer sequences.
Exactly.
Yeah.
Exactly.
Okay, so we talked about the model, we talked about the data, we talked about the training process.
Yeah.
Now let's talk about how well DeepCoder actually performs when it's evaluated on different benchmarks.
Yeah.
So we know that it gets a 60.6% pass at 1 accuracy on LiveCodeBench.
Right.
What about other benchmarks?
So they also evaluated on Codeforces.
Okay.
Which is, this really popular competitive programming platform.
Yeah.
And they get a rating of 1936.
Wow, that's really good.
Yeah, and that corresponds to a percentile of 95.3.
So, in the top 5% of all Codeforces users.
Yeah, exactly.
Wow.
Which is really impressive. I mean, that means that it's performing at the level of, really skilled human programmers.
Yeah, that's amazing.
So how they do that is they actually use this benchmark called QuinCodeElo.
Okay.
Which is specifically designed to evaluate coding models on Codeforces problems.
Okay.
And it consists of 408 problems.
Okay.
And they're all taken from 57 different Codeforces contests.
Okay.
And so they run DeepCoder on these problems.
Okay.
And then they calculate its rating based on its performance.
Okay.
And they actually use the same rating system that's used by Codeforces.
Oh, okay.
So it's a really accurate measure of how well the model would do if it was actually competing on Codeforces.
Yeah, that makes sense.
Yeah.
And they also evaluated DeepCoder on Human Evil plus Thigh.
Right. It did.
Which is another popular benchmark for code generation.
Right.
And they got a pass at 1 score of 92.6%.
Yeah.
Which again is really good.
Yeah, that's a very strong result.
And this wasn't a model that was specifically trained on Human Evil plus problems, right? This was just a model that they trained on their own data.
That's right.
And it was still able to generalize
exactly
really well.
Exactly. It's testament to how well they're curating this data.
Yeah.
And to how good their training process is.
Yeah. And what I thought was really interesting was they also evaluated DeepCoder on a math competition.
Yeah.
The AME 2024.
Yeah.
And it got a score of 73.8%.
That's right.
Which is like a 4.1% improvement over the base model.
Right.
Even though it wasn't like explicitly trained on any math data. So that suggests that like the training that they did for code generation is actually like helping it to learn more general reasoning skill.
Yeah.
That can be applied to other domains.
Exactly. I think that's one of the really exciting findings of this paper is that,
yeah,
you know, by training on code, you're actually training these models to think more generally.
Yeah.
And to solve a wider range of problems.
Oh, okay, cool. So the last thing I wanted to talk about is some of the system optimizations that they made.
Yeah.
So you mentioned this Virl pipeline thing that they developed.
So they're using Virl, which is an open source library for doing reinforcement learning from human feedback.
Okay.
And they found that Virl was actually really slow for their use case.
Okay.
Which was long context RL training.
Right.
So they developed this thing called Virl pipeline.
Okay.
Which is an extension of Virl.
Okay.
That's specifically optimized for long context RL training.
Okay. And what were some of the optimizations that they made?
So one of the big things that they did was they parallelized the reward calculation.
Okay.
So in the original Virl implementation, you would generate a bunch of samples and then you would calculate the rewards for all of those samples at the end.
Okay.
And that could take a really long time, especially for coding tasks.
Okay.
Where you have to run a lot of unit tests.
Right.
So what they did in Virl pipeline was they calculated the reward for each sample as soon as it was generated.
Okay. So they didn't have to like wait for all the samples to be generated before they could start calculating the rewards.
Exactly. And that really sped things up.
Okay.
Because they could be calculating the rewards in parallel with the sampling.
Gotcha.
And they also made a number of other optimizations.
Okay.
Like they improved the way that the samplers were managed.
Okay.
And they also optimized the way that the data was transferred between different parts of the system.
Gotcha. And all of these optimizations together resulted in like a significant speed up in the training process, right?
Yeah, they saw up to like a 2.5x speed up.
Wow. That's a lot.
In some cases.
Oh, yeah.
Yeah, that's huge.
So that's really important, right? Because like, if you can speed up the training process, then that means you can experiment with more different models and architectures and you can try different things.
Exactly. Yeah, it just makes the whole process much more efficient.
Okay. So we've covered a lot of ground today.
We have.
We talked about the DeepCoder model, the data, the reward system, the training algorithm, the different benchmarks that it was evaluated on, and some of the system optimizations that they made.
It's a very thorough paper.
Yeah, it is.
Yeah.
So I guess like the final question is, what does all this mean for the future of AI in code?
I mean, I think this paper shows that we're getting really close to having AI models that can write code as well as humans can. And that's a really exciting prospect.
Yeah.
I think it has the potential to revolutionize the way that we develop software.
Yeah.
And, maybe even to create new kinds of software that we can't even imagine right now.
Yeah. I think that's a really great point. And the fact that this project is open source, I think is it's really exciting because it means that like anyone can take this and run with it.
Right.
Yeah.
Yeah.